Today we're going to continue our discussion on equilibrium by bringing up the concept of Le Chatelier's principle. In Le Chatelier's principle, we're looking into how when you disturb a reaction that's already at equilibrium, how that reaction responds to reestablish a new equilibrium. We'll start with a quick list of the learning objectives of this video. First of all, we'll do a quick recap of what equilibrium is all about. We'll then explore the scientist Henri-Louis Le Chatelier and what his contributions were to this process. And finally, we'll focus on Le Chatelier's principle itself. We'll cover the main idea of the principle, and we'll talk more importantly of its application. There are basically three main characteristics that affect a reaction at equilibrium. We'll go through each one of those one at a time and talk about how those changes affect the behavior of the reaction. Last but not least, we'll end up this discussion with a couple quick examples to get your feet wet a little bit. Obviously, in class, we'll spend more time covering some examples of Le Chatelier to give you some more practice. Over on the right, you see a picture of a seesaw here with the reactants and products on it, and this is the basic idea you want to keep in your head throughout this video, the idea that equilibrium represents a balance, and when you disturb that balance, this reaction will have to change in order to reestablish it. Here we can see that this disturbance here has caused the reactant side to be too heavy, to stick with our analogy, which will result in the production of more products in order to rebalance our balance beam. Like I said, this is just an analogy, but it's a picture you want to keep in your head that will help you explain this concept of Le Chatelier. To begin with, we'll start with a recap of the general concept of chemical equilibrium. If this is something you need more background on or the slide doesn't give you enough info, please refer back to the chemical equilibrium video to make sure you know what you're talking about. First of all, we have equilibrium reactions occur where reactions, the forward and reverse reaction, are both spontaneous, meaning once you produce some product, the product spontaneously breaks down to reactant, the reactant spontaneously combines back together to make product, and we get this constant back and forth. The forward and reverse reaction rates then, once these forward and reverse reaction rates start, change as the reaction progresses, and they'll keep changing until eventually both reaction rates are equal, meaning the forward reaction rate happens at the same exact speed as the reverse reaction rate. And we call this point in time where these rates are equal, equilibrium. We also think of this equilibrium as being a dynamic process, and that's not because what we see is that the reactants and products stay constant, but the forward and reverse reaction are always constantly running. So we're constantly making product, we're constantly making reactant, but the quantities of those two substances remain relatively constant. Last but not least, we can express this equilibrium concept with what's known as the equilibrium expression, which is this equation down here in the bottom left. If we have a reaction AB reacts to make CD, we take the concentrations of the two reactants, put them underneath the concentration of the two products, and the ratio of products to reactants gets expressed in this value here, KEQ. And by looking at this value, KEQ, that can determine for us where the balance of this reaction actually ends up forming. So before we dive into the concept itself, we'll talk a little bit about the scientists involved. As always, the scientist is not something you're necessarily responsible for covering in your tests and whatnot, but it is something I like to throw in there. The scientist in question today is a scientist by the name of Henri-Louis Le Chatelier. Henri-Louis Le Chatelier was born October 8th, 1850. As you might have guessed from his name, he was a French chemist. His original training actually followed in the footsteps of his father, who was a metallurgist, a metals engineer, or materials engineer, and he actually had a lot of success in that field. But through his work and the process that he did, he started to become more and more interested in chemistry and actually turned to teaching chemistry later in his career. Ultimately, through his work, he came up with the concept of Le Chatelier's principle. Not named by him, of course, but that's what people called it afterward. And the question that Le Chatelier's principle really answers is, what effect does changing reaction conditions have on the equilibrium position of our reaction? Now, unfortunately, Le Chatelier was born before the Nobel Prize era, so he did not receive those types of prizes. But Le Chatelier was recognized as being a member of the National Order of the Legion of Honor, one of the highest honors that can be given in the French government. There's actually ranks that go along with this position too, depending on the contributions you've had to society, and Le Chatelier actually rose pretty high in the ranks. He got pretty much to the second highest rank they possibly offer. So again, no Nobel Prize for this scientist, but definitely recognized for the great work that he did for his country and for chemistry as a whole. Let's dive then right into Le Chatelier's principle itself, talk about what it is and what it means in terms of reactions at equilibrium. We'll start with a formal definition of Le Chatelier's principle. When a change is opposed on a system that is already at equilibrium, meaning the system has already established that balance, the forward and reverse reaction rates will change in a way that reduces the effect of the change that you imposed on the system. So if you do one thing to a system, the forward and reverse reaction rates will change to undo it. I find for a lot of people that first definition is a little tough to stomach, so let's talk about this in a couple different ways. Another way of saying it that takes away some of the heavy vocabulary is that if you disturb a reaction that's at equilibrium, the reaction will act in a way to reestablish a new equilibrium with these new conditions. Again, let's get a little bit more specific. If you change a reaction so that the forward or reverse reaction speeds up or slows down, the reaction will respond, and this is the key term here, by doing the opposite. So whatever I do to my reaction, the reaction does the opposite, and the reason we do the opposite is because this will help to reestablish the equilibrium we're looking for. And this here might be the best definition of the three of them, simply because I think it's just the easiest to digest. All three definitions kind of all say the same thing. The question is, or the real goal is, whatever you do to your reaction is going to do the opposite. And again, the goal of that being to reestablish the equilibrium that used to be. Moving ahead with Le Chatelier's principle, let's talk about some factors that can disturb our equilibrium. Remember that last slide was all about changing the equilibrium. Let's talk about some things that actually do that. The quick list we have here, and there are more than this, but these are the ones we'll be focusing on. First of all, changes in concentration. If I add more reactant or I add more product, we can expect that to change the balance of our equilibrium. Secondly, we can talk about changes on volume or changes in pressure. And again, in certain conditions, these can affect our equilibrium as well. And finally, the last one on the list, changes in temperature. If I increase or lower the temperature, again, that'll change my equilibrium. In all three of these cases, no matter what kind of change I make, my reaction has to do something to counteract that change to reestablish the balance it originally had. For each of these, we're going to go through these one at a time, how concentration, volume, and temperature changes things. We have to do a couple things. We have a couple objectives. First of which, we're going to explain how the reaction will reestablish equilibrium after each one of these changes. And then again, we have some key words here, the idea of reestablish equilibrium. We're going to explain how this shift will affect concentrations, how it's going to change the concentrations of the reactants and the concentrations of the products. And finally, we're going to provide a chemical reasoning for why each of these changes actually occurs. When I do this to my reaction, what's the reason that it responds in the particular way that your reaction responds? As I said, we'll go through each of these one at a time, and by the time we're done, you'll have a pretty good toolbox in terms of figuring out how Le Chatelier's principle applies in a bunch of different ways. Let's start that process of going down our list, and we'll talk about how changes in concentration affect the equilibrium of a reaction. Out of the three, I think this one's the easiest to understand. So again, we'll start by talking about how the reaction will reestablish equilibrium. If you add a reactant to the system, so if a reactant is added to our system, at equilibrium, the system is going to shift away from the component added. So if you add reactant, the system is going to shift to products. If you add product, the system is going to shift to reactants. If you remove things from your reaction, the system is going to shift towards what you removed. If you take chemicals out, the system is going to reestablish equilibrium by replacing the chemical that you removed. So the forward or reverse reaction will happen to replace what's removed. Now we can talk about, again, the effect on concentrations. If you add reactant into your reaction, that's ultimately going to speed up the forward reaction rate. That sped up forward reaction rate is going to consume some of the reagent that you reacted and means the concentration of your reactants goes down, and that's going to ultimately create more product, which means the concentration of our product goes up. And notice what we did up here is somewhat, at least, undone by what the reaction does to respond. And again, that's Le Chatelier's principle. Whatever you do to the reaction does the opposite to counteract. Let's talk about an explanation for this, and this explanation is the easiest of the three because, again, it's based on the basic concept of our equilibrium expression that we've already talked about. If, say, for example, I add in a whole bunch of chemical A, that's going to make this value right here shoot up, and as a result, we will no longer, our expression here will no longer be equal to our equilibrium constant. The reaction is going to respond then by undoing this, and it's going to force the reaction to happen in the forward direction more, which is going to increase the value of C, it's going to increase the value of D, it's going to decrease the value of B, and decrease the value of A, until eventually you're going to have all these changes occur, so that we'll get back to equaling the value of K again. So as we can see, because of the change we made up here, it's going to have the reverse response and change and push the reaction to reestablish equilibrium, and that can be shown mathematically. Likewise, we can do the opposite. Let's say, for example, we remove some of chemical B, we pull it out of our reaction. That's going to lower this concentration, and again, now all of a sudden our equilibrium expression here will no longer equal the value of K. Well, the reaction will respond then by running more in reverse, so that C and D go down. We're going to reduce, let's change colors here. We're going to reduce the amount of C, we're going to reduce the amount of D, we're going to increase the amount of A, and we're going to increase the amount of B, until eventually, again, our values become equal again, and the ratio here of products to reactants goes back to equaling our value of K. So in each case, adding or removing, we can very clearly see how the equilibrium expression shows to us what has to happen to our reaction in order to reestablish equilibrium. Moving on, let's talk about how changes in volume and pressure are going to affect the equilibrium of our reaction. The first thing to note, and this is something people make mistakes with all the time, is that it is only relevant if there are gases present. If there are no gases present, then a change in volume and pressure will have no effect on the actual equilibrium of the reaction. So this is only relevant with gases, and maybe we should actually write that in over here. These types of changes have no effect if there are no gases present. So keep that in mind. It's a neat little booby trap we can put into questions sometimes. So, now that we've established that, when you change things like volume and pressure, let's talk about how that reestablishes our equilibrium. A decreased volume or an increased pressure, and if you remember your gas laws, this is pretty much the same thing. When volume goes down, pressure goes up. Both of these scenarios are going to force our molecules to be closer together than they would naturally be. So that's what's going to happen. To reestablish equilibrium then, we're going to want to undo this. So the effect then it has on concentration, Le Chatelier will predict that our reaction will move in a direction to allow our molecules to spread out to get back to their original spacing. So whatever the reaction can do to undo what happened up here is what Le Chatelier's is going to predict. This movement then, either in the forward or the reverse direction, is determined by the number of moles of gases. And this is probably the most important thing in the whole list here. This is determined by the number of moles of gases in the reactant or product. By changing the number of moles of gases, that's going to change the spacing and get us back to the original condition where molecules are spaced more naturally. Now let's see if we can explain this a little bit. And to explain it, I have a very famous equilibrium reaction here. This is nitrogen dioxide reacting to form dinitrogen tetraoxide. This is very famous because in this particular scenario, it's only one reactant and one product. And the neat thing about the two of these is they're very, very different in color. I believe this guy here is more clear, whereas this chemical here is more brown, meaning we can see shifts in the equilibrium process. Well, if we decrease the volume of this scenario, if we have these gases locked in a tank, that's going to cause these molecules to squish together. And again, they're going to be tighter together than they would normally want to be. As a result of that, this reaction is going to start producing more product. It's going to shift in this direction. The reason this happens is because more forward reaction reduces the number of moles and gas in the tank. And we can see that clearly from the coefficients here. When I have my reactant molecules, there's 2 moles of nitrogen dioxide. When it goes to make product, it only turns into 1 mole of gas. So the more forward reaction we have, the fewer moles of gas are present in our actual tank. And if we think back to our equation, PV equals nRT, if the reaction can reduce the number of moles of gas in the tank, that's going to reduce the pressure in the tank, and it's ultimately going to get us back to that condition where we have our molecules spaced out more regularly. So we increase the pressure, the reaction shifted in a way to reduce the number of moles, and that reduced the pressure back down again and got us back to close to anyway, our original conditions. So just to be clear, it has to do with the number of moles of gases in our reactant and the number of moles of gases in our product. Whichever one of them has more or less is going to determine where we shift based on increasing or decreasing pressures or increasing or decreasing volumes. Last but not least, we'll discuss how changes in temperature are going to affect the equilibrium in our reaction. This equilibrium scenario is actually dependent entirely on thermodynamics. One of the reasons I love Le Chatelier's principle is because it forces us to go back and look at a lot of science from earlier in the year. In this case, we're going to be dealing with our thermodynamic scenarios. An exothermic reaction, one that gives off heat, is going to prefer colder surroundings. That's a place to give that heat off into. Whereas an endothermic reaction is going to prefer warmer surroundings. Remember, endothermic reactions need heat from the outside, and that's going to provide them, those warm surroundings, with the heat that that reaction actually needs. So then what effect does this have on the concentrations as we do things like changing temperature? Well, one thing we should say is that when you're reversing the reaction's direction, forward versus reverse, we're reversing the signs of delta H. We change an exothermic reaction into an endothermic reaction, or an endothermic reaction into an exothermic reaction. And if you recall, we talked about this a lot when we were dealing with Hess's law. You could reverse a reaction and it reversed the sign of delta H. This is going to then favor the forward or reverse direction depending on whether the temperature is high or low. So the forward or reverse reaction is going to happen in order to get back to these favorable conditions that we talked about up here. Let's talk about an example. Here we've got iron metal reacting with oxygen gas to create iron oxide, Fe2O3, and in this case the delta H for this reaction is negative, meaning this is exothermic. This reaction is going to give off heat. So we'll say over here that heat is released in the forward reaction. So if I were to increase the temperature surrounding this reaction, that would actually favor the reverse reaction. The increase in the amount of heat is going to provide more heat energy available for the reverse reaction to occur, and therefore that reaction will start to speed up and the forward reaction will start to slow down. So the reverse reaction is endothermic because the forward was exo, and is more available heat means that that reaction is more favorable. It has the heat needed to run. Likewise, a decrease in temperature will most likely favor the forward reaction in this scenario. As we drop the temperature and make it cooler, the reaction is going to move forward to replace some of the lost heat from the dropped temperature. The forward reaction is exothermic, meaning it releases heat, and that heat's going to move from areas of high concentration into the areas of low concentration, which is now our cooler surroundings, because we've decreased that temperature. So again, using some factors or some information about the reaction itself, we can apply Le Chatelier's principle to see how temperature affects the behavior of our equilibrium. To wrap things up, we're going to go through a couple examples. I'm going to pull a reaction up on the board plus a couple changes. Your job is to take a moment, apply Le Chatelier's principle, and see how it affects the results. I'll go over the answers and then we'll have a second example right after that. Here's our first one. Pause the video. Your job is to predict what will happen in this reaction if I add chlorine to the reaction, if I increase the pressure, and if I increase the reaction temperature. So hopefully you've had a chance to give this problem a try. Let's go over some answers really quickly. The addition of chlorine gas over here is going to make the reactant side higher than it should be. As a result, in the equilibrium expression, as a result, the reaction is going to move in the forward direction preferentially in order to decrease these concentrations and increase these concentrations so we get back to the ratio that matches our equilibrium constant. So this is going to favor the forward reaction. An increase in pressure is only going to affect things when gases are present. The only gas present in this scenario is the chlorine gas itself. If I'm going to increase pressure, again, the reaction is going to favor the forward direction to reduce the number of moles of gas that we have in order to bring that pressure down again. So this again will favor our forward reaction. And then last but not least, an increase in reaction temperature. If I put this reaction in a hotter vessel, the reaction itself is exothermic, meaning it gives off heat. An increase in temperature then will favor the reverse reaction process. That increased heat that we have is going to make the reverse reaction have more available energy, and as a result the reaction will happen backwards faster than it happens forwards. So we'll say that this was going to favor the reverse reaction. Here's our second example then. What I want you to do is the same exact thing. I've got the reaction below. We've got the appropriate delta H values. What's going to happen to this reaction if I remove carbon dioxide? What's going to happen if I increase volume? And what's going to happen if I reduce temperature? Again, pause the video, give these a quick thought, and then we'll go over the answers in a second. All right, let's talk about some answers for this. If we start removing carbon dioxide gas, that's removing this one here. We're going to reduce the concentration of the reactants. The reaction is going to respond by replacing what we took out by increasing the forward reaction. That's going to bring the concentration of reactants down, the concentration of products up, and ultimately will reestablish equilibrium. This again will favor the forward reaction. If we increase the volume of the tank, that's going to same as decreasing the pressure. That's going to cause our molecules to spread out a little more. Your reaction is going to want to replace those spread out molecules and fill up the space. Again, this applies when we're dealing with gases here, but the interesting thing here, oh, we have a little typo here, wait a minute. This is solids. Again, the only gas present is our carbon dioxide. So that means, again, the forward reaction is going to happen faster to create more gas to fill up the increased space that we had here and bring that pressure back to the original conditions that it was. So again, this is going to favor the forward reaction. Last but not least, we're going to reduce the reaction temperature in this case. This reaction, unlike the last one, is endothermic, which means a higher amount of temperature or higher amount of heat energy is going to be providing more energy for this endothermic process. And just like the other two, this is going to favor the forward reaction more, and it's going to cause more product to be formed. So as we have more heat, that's more energy for our endothermic reaction to use. It's going to favor the forward process. So I'll write that in, forward. And that's pretty much it. We'll go over a quick list of the things you should be able to do now. First of all, you should be able to explain Le Chatelier's principle and how it's related to chemical equilibria. You should be able to predict what will happen when you alter things like concentration, pressure and volume, and temperature. If I change this, what effect is it going to have on my reaction? And then last but not least, you should be able to provide a chemical explanation as to why those changes actually occurred. My temperature went up, it caused the forward reaction to happen faster, and this has to do with that value of delta H. As always, we'll take some time in class to practice these a little bit further, and hopefully by the time we're done, you'll be able to apply Le Chatelier's pretty quickly and pretty easily.